All right, so picking up where we left off last time, we looked at a selection sort, and then you implemented selection sort in your lab yesterday, and then you quickly saw, or at least we saw from the demonstration on Monday, that this is not an acceptable sorting algorithm, because sorting anything like, a billion elements or something is going to take 20, 30 years. So we went over and changed it to quicksort. And in fact, we used the built-in version of quicksort when you did, and then you switched over to that in your lab as well. And we saw that quicksort, something that would have taken 33 years, only took about 3 minutes with quicksort on the examples that we were using. It uses a divide and conquer strategy. We described it as finding or taking a pivot element, say the first element, and then putting everything that is less than that element to the left, everything that is greater than that element to the right, and then you recurse on each one of those sides. That's how it's quick, right? It's a divide and conquer kind of strategy. And its performance only requires about n log n operations. And we saw that held true. If we want to look at the analysis again, we can, but otherwise that's in comparison to n squared operations. And so if you just take one of those terms, right, ignore the common term of n, and look at n versus log n, that's the difference between linear search and binary search. One is exponentially faster. And that's where you get the difference of 33 years versus 3 minutes. All right? So what I wanted to do with the rest of the day is go back and get some more practice, as well as highlighting some potential pitfalls that you might face when you're writing your own comparators and searching and sorting stuff. And to do that, I'm going to bring in our old book demonstration over here. Remember that a book is a title, an author, a published date, and a rating. And an author is a first name, last name. And we've got a year, month, and a day for the actual published date here. We've already loaded up our old CSV data, and I printed stuff out. In fact, let's go ahead and get rid of all of the rest of this, because we're not going to. I'll just comment it out for now, and then we'll go ahead and compile everything together and take a look at. Oops. Oops, not 0. I. All right. Otherwise, we're always printing the first one. All right. So let's take a look at our data before we start mucking with it. All right, so I've got all this data from Harry Potter and the Deathly Hallows all the way down to a Game of Thrones. All right. Now what I want to do is I want to sort it, but I'm not going to write my own sorting algorithms because I've already learned the way to do this is to use QSort. Right. Now remember what QSort looks like. QSort. Let's just look up the man page on it. Right. It requires 4 arguments. The first argument is the thing that you want to sort, the array that you want to sort. And it is generic so that you can sort an array of books, an array of integers like we've already done, etc. And it's not const. Remember, if you put the const keyword in front of it, that means that you're promising that you're not going to make changes to it, but QSort certainly is, right? The absence of a const keyword here is basically advertising the fact that it is going to change your array, right? So let me go ahead and put in the array that we want to sort, books. That's what I loaded up from the CSV file, okay? The second argument is, like all arrays, you have to tell it how many elements are in that array, right? We've been doing this ever since we started with arrays. You always have to tell it how many elements are there. And that's being loaded up by that same function in numbooks, number of books. The next one, the third one is the size of each element, because if quicksort is going to be exchanging elements, there's this thing over here and this thing over here, and they're out of order. They need to be swapped. It needs to know that this thing is 4 bytes and this thing is 4 bytes so that it exchanges those 4 bytes. Or that this thing is 40 bytes and this thing is 40 bytes so that it exchanges those 2 big chunks. Because it doesn't know anything else about what those things are. So we're going to have a use size of book, right? Because that's the size of each element that is being stored in that array. And then finally, the comparator that you want to use. I don't have any comparators here yet for books, but let's go ahead and write one, using what you learned yesterday in your lab, right? So first of all, int compare book. We'll do it by title because that's the easiest, by title. Right? Now, do I pass it in 2 books, book A and book B? Is that a comparator? No. It is only a comparator if you are taking 2 const void star pointers, all right? 2 generic void pointers. What you do inside step one is to cast those as the type that you want. When we did that with integers, we did it like this. We forced them to become integers. Well, these are not integers. I want to force them to become books. Book X and book Y. Book X and book Y from book A and book B, respectively. Now that I have got them, now they're in my hands and they have been forced to become books. Okay? So now I can look at the title. So if X title is less than Y's title, right? Now my first question here is, why did I use the arrow operator here? This is the X right here. That is a structure or a structure pointer. Structure pointer. Therefore, that's why we need to use the arrow here. Now, can I use, my second question is, can I use the less than operator there to compare a string to a string? Nope. I mean, I can, but it would end up comparing a memory location. So strcmp is how I compare strings. That returns, if you remember, something negative, something positive, or 0 depending on the relative ordering. So if that's less than 0, I need to return something negative. If it's greater than 0, then I need to return something positive. If it's 0, then I need to return 0. Should I even be writing this if statement then? Nope. Let's just return whatever strcmp value that is. Right? Why write many lines of code when few lines of code do? Right? So let's go ahead and use this now that I've got this compare book by title. I'm going to print it out once, and then I'm going to print it out a second time after I've sorted it. And just so that we can clearly see things, let me go ahead and put in some ASCII art here. There we go. Some separators so that we can see where the original is and where maybe a bunch of white space right around it. Make it look nice and pretty. There we go. Oops, what's wrong? I forgot my semicolon right there. There we go. All right. strcm, if I'm going to start doing string stuff, what do I need to do? Bring in the string library. There we go. All right. Now let's run it. On the first run, on the first printout at least, you'll see the original order of the data. On this run, you see that it has been sorted according to the title of the book. Now, the title of the book here, it has a bunch of articles, right? A, an, the. Normally, if you were to sort this in alphabetical order, you would ignore articles so that A Game of Thrones would actually appear under G, right? Or the Clan of the Cave Bear would actually appear under C, because you usually ignore articles when you're doing that. But, of course, strcmp is not doing that, right? If I wanted to compare book by title ignoring articles, what would I need? A lot more complicated stuff here. I would have to look and see, does it start with an A or an or a the? If so, go ahead and remove that and then sort it with respect to strcmp. I'm not going to go that far today, right? But that's by title. How else could we sort these things? I want to find the best book. So how would you go about finding the best book? Sort it, right? Sort it in descending or ascending order. Ascending? Okay, then where would the best book be? Either or, it doesn't matter. If you go descending, then that means that the best book is at the top. If you go ascending, then that just means that the best book is at the bottom. Right? So which one do you want to do? Descending? Okay. Ascending is usually the natural ordering, right? That's why integers ascending order. So usually if I were to do this by rating, I would actually label it as desk, descending, right? If it were ascending, you could do ASC for ascending, but that's the usual, so you just leave that off. So I'll go ahead and call this descending, okay? Same pattern as before. I receive those two books, things, and I force them to become books so that I can check out their rating, right? So here's a pitfall to avoid. Do not, oops, come on. Oh, my entire computer is locked up. Okay, there we go. Do not, blah, blah, blah. Do not rely on the difference trick, right? So the difference trick is as follows. What I could do is I could return the difference between their ratings. So let me go with y's rating minus x's rating. And again, why did I use the arrow operator there? Because they are pointers to structures. Now let's think about this for a second. What if x had a rating of 4.5, right, and y had a rating of 5.0? Are they in order or out of order according to descending order? They are out of order. So I would want to return something negative. So what is the result of 5.0 minus 4.5? Or sorry, they're out of order. I would want to return something positive, right? They're out of order, so I want to return something positive. Well, what would that be? Using this difference trick here, where I just take the difference. 0.5, right? That's positive. So, should I just return that? Remind me, what is the return value here? An integer. What happens to this 0.5? Truncation, giving me what? 0. Let's try it. Of course, all of that was just comments here. GCC. Oh, you know what? I don't think I'm using it. Let's go ahead and go down here and actually use it now. Right? GCC this. And let's go ahead and list everything out in descending order. It looks kind of like descending order. 4.62, 4.55, that's okay. But then what do we have right here? 4.58. Why? Because the difference between 4.50 and 4.58, when you truncate it, is 0. There's no rhyme or reason between these two, right? The difference between this one and this one, when you truncate it, is going to be 0, right? So, did that get us what we wanted? No. Don't do the difference trick. It doesn't even work with integers, right? So, for example, what if I did, say, year instead? Actually, let's fix this first. Don't rely on the difference trick. Do an explicit if-else condition here. So, if y's rating is now I'm going to go x and y because I always think left to right, not to right to left. All right. So, if x's rating is less than y's rating, then they are then they are in order, right? Oh, no, we're going descending order, so they're out of order. So I'll return 1. Right? Else, if x's rating is greater than y's rating, then I'll return something negative. Otherwise, return 0. Well, let's make sure that it works before we move on and fix other things and show other things. Oops, not R, Y. There we go. And let's run it. Okay. Now, where's the best book? All the way at the top, 4.62. What about all these other ratings here? Are they in order? Looks like it to me. And then there's the worst book down at the bottom. Okay. Probably should be even lower than that. Anyway, let's see. What else? Oh yeah, it doesn't even work with integers because it's susceptible to overflow. Suppose that I tried to do it with integers by going x minus y, and these were not doubles, so I'm not going to have truncation issues anymore. But what if I had, say, 2 billion minus negative 2 billion? Right? Hopefully that's still working, right? What's the mathematical result of that? 4 billion. Okay, I'll buy that. Can you store 4 billion in an integer? No. What happens when you try to store 4 billion in an integer? Do you remember overflow? How overflow actually works? It wraps around to the negative part, right? And when it wraps around to the negative part, instead of giving you something positive, it'll end up giving you something negative, right? So tricks like that, don't do them. Tricks are for kids. Actually write your own if-else-if statement here. And also follow this pattern. Less than, greater than, and then 0 is always the third option, the else option there, right? I suppose if you really wanted to, you could compute the difference in a stored variable, but you'd still have an if-else condition here checking that variable. So you're only adding one more line of code, and you're not getting you're not getting anything out of it. Right? So avoid the difference trick. Okay. So avoid the difference trick. All right. It is susceptible, if that's how you spell it. No, susceptible. There we go. Susceptible to overflow and truncation. All right. Instead, always write explicit if-else conditions, or use other functions. Right? Truncation. Right? Functions. There we go. Okay. How else would you want to sort these books? By author. All right. Let's come over here and do it by author now. In fact, let's do it by author, then by title. So, int compare books by author. And then, because I have several Frank Herbert books or several Terry Pratchett books, I want to go ahead and sort them by, if I've got the same author, I want to sort that sublist using some other criteria. So by author, then by title. But we don't usually write functions that long. So by author, then title. Author, title. Right? So once again, I will go ahead and cut and paste this pattern. Right? Great. Now, how do I go about comparing the author's last name and then their first name? So I would want to use strcmp again on X's author last name, and compare that to Y's author last name, right? Author dot last name. So two questions here. I'm obviously I'm using the arrow operator here because these are pointers, but why am I using the dot operator here? Let's come over here to book and remind ourselves of how we define this. Person, once I'm in the book, is that a pointer right there? Nope, that's a regular old structure. So I have to use the dot operator. All right, I could have a big giant if-else-if statement here. If strcmp is equal to 0, then that means that they have the same last name. So I need to look at the first name. If, right, strcmp, last name, right? Last name, first, there we go, and first, there we go. Right, I could. This is called nesting. There's nesting hell. I forget what it's called. There's a phenomenon where you can write bad code and you just have nested condition after nested condition after nested condition. Here I have three criteria: a last name, a first name, and then a title. What if I went even further? What if I went then by year and then by something else? Right? Then I'm going to have 5 nested if conditions. Right? Don't do that. Instead, you want to flatten your code out. To accomplish that, what I'm going to do is I'm going to store this into a variable, int result. Now, only in the special case where that is 0 do I need to break a tie. We've got Pratchett. Then we need to go, let's go with Herbert because we've got Brian Herbert and we've got Frank Herbert. We then need to go to the first name. So if we have a tie, then if result is equal to 0, then and only then do we go to the first name. But we don't use a bunch of if-else conditions. Instead, we just have a result. We reassign the result, right? All right, and return result down here. Okay. Now, if you want another condition, instead of having a nested if-else-if condition, you just have another if statement. If result is still 0, what does that mean at that point? We've got an author with the same last name and the same first name. So how do we break that tie? The way I wanted to do it here is with title, right? So what do we do again? Result is equal to strcmp of X title and Y title, right? In other words, I don't have to nest these things, and get very, very complex code. I can flatten it out. If you want another condition, say that it's the same last name, same first name, and same book. Maybe there's a different edition. Then you would go to the year. The one released in 2000 is different than the book released in 2005, something like that. But it doesn't require this nesting. It just requires you to see that there was a tiebreaker and that you needed to break the tie. There was still a tie, so you needed another tiebreaker. There was still a tie, and you needed another tiebreaker. Right? Why did I not use else if, by the way? Just read that logic to me. If result is 0, then do this. Else if result is 0, do this. Does that sound right? I want two different things under the same condition? No. I want to check these things and have follow through. If there's still a tie, break the tie this way. If there's still a tie after that, break the tie that way. Right? This is much, much better code, not nesting code like a bunch of Russian nesting dolls. It gets way too complicated. All right, let's go ahead and try that and see if it worked before we move on. Let's compare book by author. There we go. GCC. A.out. There we go. Let's clear it first and then A.out. All right. All right, so let's look at it. So we've got the original data there. And here we've got by author. So there's Jean Auel at the top and J.K. Rowling at the bottom now. But if you look at things that are the same author, Frank Herbert here, then you look at the titles, and the titles are now sorted. What if you wanted by author in ascending order, but then titles by descending order? All you have to do is write yet another comparator, right? Okay. Well, not that we have it, but what if there was another tie? If the result is still 0. In fact, what if I just did every single possible piece of data, right? And I just got down to where this piece of data is exactly this piece of data, right? That's what's called a partial order versus a total order problem, right? So other issues. In fact, to illustrate this, let me come over here and show you a demonstration that I've set up. This is a bunch of roster data. We've got a first name, last name, an NUID. These are all fake people. Actually, these are real people, but they're ball players, not UNL students. Really old, not really old ball players. Some of them are still playing. But then we've got a year for them. We've got their GPA. We've got the course that they're currently taking and a course name. I've got a bunch of different ways that you can go ahead and sort them. I'm going to sort them by their first name, last name. First of all, observe that they're not sorted by their first name, last name yet. Okay? Let me move this over. There we go. All right. When I hit this sort button, what do you think is going to happen? It's nicely sorted by last name and then by the first name. See, Baez up here, then Castro, and then all the way down at the bottom, Sandberg. If I hit this button again, would you expect any changes? Sorted again by the same criteria. Sorted again by the same criteria. Would you? Would you want it to change at all? Same exact criteria, right? Sorted again by last name, first name. Well, it's already sorted that way. You probably should leave it alone, right? What's going to end up happening if I just keep hitting this over and over and over again? Is it changing anything that matters, like the last name, first name? Nope, Javi Baez is still there at the top, all three records. But it starts unstably going back and forth here, right? And the reason for that is because we've got what's called an unstable sorting algorithm. If you have values, for example, here, let me go over here, other issues. You generally want stable sorting algorithms or implementations, right? That is, if you sort 2, 4, 2, 1. The result should be 1, 2, 2, 4, right? But with the original two values in their original relative order. In other words, what I'm going to do is I'm going to label them as A and label them as B, right? So that when you sort them, the one that said A first should stay first. The one that said B should stay second, right? It would be unstable if the algorithm can end up with, say, 1, 2, B, 2, A, and 4, then it is unstable, right? And this can be avoided if you use what's called a total order, right? You can avoid sorting instability by defining can't type today. Defining a total order, right? In other words, no matter what, you have an ultimate tiebreaker, right? Instability. Is that instability? All right, yeah, there we go. All right, now I got it. All right. You want an ultimate tiebreaker so that you don't have this kind of back and forth thing right here, right? When I sort it like this, it's a bunch of things just keep going back and forth, back and forth. Again, the reason that you would want something like this is because if you sort it by one category and then sort it by another category, this is especially true in Excel, right? And in fact, in Excel, if you want to sort a set of data, you usually bring up this dialog that says sort by this column. Then you have a plus button where you can then sort by this column, then sort by this column. Think about your grades, right? How would you want to sort them? You'd want them sorted by a semester, and then within that you would want to, you want to sort them by a semester, and then A to B to C or whatever. If you went to top to bottom or ascending, best to worst grade, it shouldn't screw up all the semester values, right? You'd want to sort it by semester so that it's temporal, so that fall 2023, spring 2024. Fall 2024. Then within that category, that's where you want to sort it as a subcategory. You don't want it to be screwed up just because you're sorting it by a different criteria. You want to use that as a tiebreaker. One way of avoiding that is having an ultimate tiebreaker so that it doesn't happen. Right? So for example, books. What would be an ultimate tiebreaker for books? Even though it has the same authors, first name, last name, same title, but different editions. How are books uniquely identified? Anybody know? ISBN, right? International Standard Book Number, I think, something like that, right? What about other media, right? There's an EIDR, right? What is it? EIDR. I never remember what it stands for. Like TV shows and movies and stuff like that. Universal Media Identifier. I don't know. Entertainment Identifier Registry. Right, that's what it is, right? What if it's people? People, social security numbers and UID numbers, etc. Right? What if you don't have anything? There's this nice little thing called a UUID, which is a universally unique identifier, right? And you can actually generate these things. UUID generator. Let's just go online here and generate one. We'll generate a bunch. Right? Let's go ahead and generate 100 of these things. Right? There. They're just random numbers that have been put through this cryptographic hash over and over and over again, so that the probability that anybody anywhere in the world at any point in time for the next billion years, right, you'd have to intentionally get a duplicate. But if you follow this algorithm, the probability that you will ever find a duplicate is infinitesimally small, right? That would be like winning every single lottery from here till for a year, right? The same probability or something like that, right? If you would have to intentionally generate or reuse a UUID like this in order to have a duplicate. Right? You can generate them over and over and over again, and I can guarantee you that you will never have a duplicate. It's based on your timestamp, it's based on random numbers generated by your computer, and then it's based on a bunch of cryptographic hash functions that it runs through, right? And it's so large, it's 128 bits. So Wolfram Alpha, tell me how many possibilities that is. 2 to the 128. There we go. There's 10 to the 38 possible values that you can have here, right? You're not going to run out. In fact, Wolfram Alpha, how many atoms in the universe? Remember 10 to the 38 times 3. Okay, so that's the number of, we're not quite approaching the number of atoms in the known universe, but we're halfway there, right? Or that's something like, not halfway there, but 30 in the exponent, we're halfway there. 38 versus 79, right? All right. If you up this, of course, to 256 bits, then yeah, you're there already, right? Or something, right? So you can have a universally unique identifier generated, auto-generated, to break that tie. These are sometimes referred to as natural identifiers because they are generated by some authority, right? And that authority is responsible for ensuring that they're all unique and that nobody gets the same NUID, nobody gets this, no book gets the same ISBN. That's why you have to actually pay for them. You have to pay to register your book or pay to register your film or whatever, because it costs money to ensure that everything is unique. Right? Universally unique identifiers are free. You can it's an open it's an open algorithm, open sourced algorithm that you can use. Right? Let's see what else. That's the difference trick, sorting stability, and total orders. Another thing that you'll, not with the books, but with other things, are artificial ordering. Artificial orderings. Right? So, for example, suppose that you wanted to sort students by year in school. Right? For example, freshmen, what comes after freshmen? Sophomores, what comes after sophomores? Juniors, and then seniors, right? And then graduates, pre-fresh, whatever you want. We'll just go with these fours. Now, what if I stored this information as a string, as strings? Right? If I did freshman versus sophomore, there we go. Which one comes first? If I used strcmp, that would be true. Freshman comes first. But what if I did, say, seniors and juniors? Say a junior versus senior. Which one of those comes first if I store them as strings? Actually, this works too. Let's go with, what do I need? Sophomore? Yeah, there we go. Senior and sophomore. Sophomore. There we go. So, sophomore comes after senior. Why? They both start with S, but their second letter is E. E comes before O. So does that jive with the order that we want? Nope. So what we want instead is an artificial ordering. Does anybody have any idea on how we could represent this data not as a string, but as something else so that we do have a proper artificial ordering? All right, numbers. What would you suggest? A 1 would be for freshmen. 2 for sophomores, right? Is there a way that I could do that in code real convenient? Enumerated types. Use on enumeration, right? So in C, how do we do that again? Type def, enum, right? And then you can put it in whatever order you want. Freshman, sophomore, junior, and senior. Now, treating those as numbers in C means that you already have this artificial ordering. A freshman comes before a sophomore, and a sophomore comes before a senior. Right? And internally, it's all a bunch of numbers. 0, not 1, 2, 3, 4, but 0, 1, 2, 3. And if you ever wanted to change it, you can come back and add graduate at the end. Right? Or high schooler, or whatever. Right? So, sometimes you want an artificial ordering, something that goes against like the usual string comparisons. In which case, it's probably best to define an enumerated type. Okay. All right. Any questions on searching and sorting? No. Any other requests for doing the books like this? By year? I don't know, what would year look like? All I'd have to do is go to the date, the published date, and then get the year, and then make that comparison. Right? By the way, the difference trick there would actually be okay, because you are not susceptible to overflow. Unless you are publishing books in the year 2 billion, or 2 billion BC, right? You're not going to have a risk of overflow. If you're publishing, if you're only dealing with books in the last 2,000 years, the next 5,000 years, it'll probably be safe. Still, though, you should avoid it in general. All right. Then that concludes the course. What are we going to do with the rest of the time? Well, first of all, I've got a whole bunch of old finals that we can bring. Otherwise, on Friday, Advent of Code starts. Right? Of course, you could always go to other events. For example, I'll probably start with 2022 or all the way back in 2015. So they've got these nice little exercises, daily exercises that start really, really simple. And then by the 25th of December, they're very, very complicated. For example, this one just has you dealing with whether or not these parentheses are properly balanced, right? So for example, I think that this goes up a floor, down a floor, then up a floor and down a floor, right? Yeah. So it's a bunch of string. It's a bunch of string representations representing actions. You'd have to read the whole thing to get it. An opening parentheses means that you go up one floor in this elevator. A closing parentheses means that you go down one floor. So if we gave you a whole bunch of parentheses like, what is this? Up, up, down, down, you end up on floor 0. You always start at floor 0. If you go up, 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 or up, up, down, 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 or I forget what I just said, up, you end up on floor 3, right? And then you're given a unique puzzle input that looks something like this, right? So you're not doing it by hand, right? These are clearly programming exercises, right? You could actually do with the day 1 or day 2 pretty simply. Let's see. All I need to do is count. There we go. Find the number of lefts. There's 3,640. How many rights? There are 3,660 or 3,360. So what's the difference there? I don't know. Pull out your calculator, then do it. But you can do little tricks like that. That's how people get to the leaderboards, right? So quickly that they just realize that they can use a tool to really quickly do it, or some Unix tool or something like that. They don't even program it. They just use pre-existing tools. What was my okay? The difference was 280, whatever that was, right? So you can get by without doing a lot of programming for this, but we will, right? So don't save that, right? But we'll do as many of these as we can. I'll live stream them all. I'll even do it in the morning session. Otherwise, we can bring in as many final exams as we want. And I'll show. In fact, I'll do at least one final to show you what they kind of look like. Last year we did. Let's see, assignments. Fall 2022. Where's my exams? Here's the final. Open with Adam. There's the final exam. You're given a bunch of weather data. That weather data is represented as a timestamp along with a temperature in Fahrenheit, and then you have to produce a bunch of reports. What was the record minimum temperature? What was the record maximum temperature? What was the mean temperature? And we're not giving you 5 or 10 samples like the example here. We're giving you millions of them, right? Then there's a data report. What is the earliest known data sample? So it looks like 2017. What is the most recent, according to this timestamp? And then a bunch of inconsistency reports. We actually give you 2 files. 10 million data points over here, 10 million data points over here. Find the one data point that's missing from one or the other, right? So for example, there's an inconsistent data. In one of the data sets, it says it's 32.78, and in the other data set, it says it's 32.9. There's a missing data from the first data set. It's missing from the second one. You have to find that needle in the haystack. How would you go about doing all of these things? Well, first of all, these reports that's just a for loop. But what about this? The earliest known sample report. Sort it, right? Sort it by date. And this is actually an ISO 8601 date timestamp, which makes it lexicographically orderable, right? And so you can just use strcmp here. Once you sort it, guess where the earliest is? At the top. Guess where the most recent is? At the bottom. Right? How would you go about searching and sorting here? Sort them by date, right? And then for each one over here, search for it over here using binary search. You're not going to do it with a regular old search with 10 million data points and 10 million data points with linear search. Why? For each point over here, each of these 10 million points, are you going to do 10 million points over here? 10 million times 10 million, how many is that? 10 million times 10 million is? 14 zeros, how many is that? 100 billion? Or 100 trillion? 100 trillion, right? Yeah, that's 100 trillion operations. That's not executing in any amount of time there. So you need to use binary search to cut it down to only a few million transactions or operations instead. That was last year's. The year prior to that was, well, he's now gone, but it was, where is it? And then, where's the handout? Darn it. Here we go. All right, so Scott Frost was still our coach at the time. And he was arguing back in 1997 that Nebraska was, if you look at yourself in the mirror and say that if your job depended on playing either Michigan or Nebraska to keep your job, who would you rather play? Right? He was talking about the fact that there were two national champions that year, Nebraska and Michigan. Why? Because they were both undefeated and they never played each other. Right? We were not in the Big Ten yet. And so what we give you is a complete list of all games that year, right? Using UUIDs as teams. There was whoever that was scored 6 points. Whoever that was scored 41 points. So obviously that team won, right? So we give you a complete list of all NCAA teams, everybody from North Carolina State all the way back down to Miami, Florida, right? Identified by UUIDs, and you have to produce a report that looks, where is it? Looks something like this, right? Where Nebraska is the clear winner here because they went undefeated. They only played 11 games back then. And Michigan went undefeated. But if you look at the point differential, Nebraska scored more than 100 points against their opponents than they scored against them over Michigan. So it was clear. It was a clear argument that if you ranked everybody by win-loss as well as point differential, that Nebraska clearly won, or should have been sole national champions that year, right? And then all the way down here, oh, poor Rutgers. They're doing a lot better now, right? What's their record this year? Was it better than ours? Were they at least 6-6? Nobody follows football. I don't blame you anymore. But anyway, you had to produce a report like this. So how would you go about doing it? Searching? No searching necessary here. I guess there is searching necessary that you need to know which team won and which team lost. So you need to go through this other file and find that team. For example, this first team here was Illinois. 6-6. Oh, wow. But strength of schedule, right? They didn't have to play CU. We did. Ohio State. So Ohio State crushed Illinois that year, right? 41-6. Right? So you'd have to look up that score in one file and update that team over in some other file, right? And so you have searching and sorting there, and then ultimately you have to sort them by their win-loss record, and then their point differential to break ties like that. So that somebody that goes 10-1 and 10-1, Florida State was clearly better than K-State because they scored more points against their team, other teams, than were scored against them. Right? We use a much more complicated formula now, but if you just use this simple formula, it's clear that Nebraska should have been national champions then. Sole national champions, I should say. Right? We can keep going back and as far as we want, but I'll let you decide on Friday. Do we want to do football? Do we want to do weather data, wherever it is now, weather data, or do we want to do something from Advent of Code here? Right? We'll do that for Friday, and we'll do that all next week as well.